Hey, بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. All okay? Good. Okay. Uh, Today, inshallah, we're going to be continuing the discussion we started last time on vector spaces. In my opinion, this is a very important lecture. Okay, if not the most important one, actually, in topic number one. If everything goes well today, and by well I mean if I do my job correctly, I should be able to celebrate breaking down all what you learned about linear algebra. Okay, so and hopefully I'll convince you that okay, you need to go learn it or relearn it or restudy it in a proper way. Okay, hopefully if I do my job well. Okay, if not, then you'll still be here, attached to linear algebra. Okay, so let's see. So today we're going to be continuing the discussion about vector spaces. Let's start as a recap as usual. We're still looking at this idea of different mathematical objects. We discussed so far sets, groups, and vector spaces over a field. The mathematical object that was in a set was simply just the set by itself. Okay, there was no extra structure. We're not able to do a lot of things by having a set except just counting the number of elements in it. That's the only way we have, and we call this cardinality. With a group, we can do more stuff. So we give the group a binary operation, and this binary operation needs to satisfy certain conditions. And so, thus, we call this pair a group. And with a vector space over a field, we introduced last time what a field was. And we said, okay, the field is a set with two operations that satisfy certain conditions. And given a field, you can define a vector space over a field by giving one set, which is the set V, with two operations, one which we call vector addition, and another one that's called scalar multiplication. And these three together, along with the over the field, they are called a vector space. And then we looked at what are the maps that respect the structure. For sets, we talked about just similar to the set that they were very just with no structure. We also looked here at maps, map between two sets, and the maps that can go back and forth, which in the end make S and T by isomorphic to each other. We call them bijection. Groups, we said that not any map would respect the group structure, and we call them the maps that respect the group structure homomorphisms. And if they are also bijective at the same time, then we call them group isomorphisms, and they make the two groups isomorphic to each other. You can go back and forth. Anything you can do with this group, you can do with that group. This is essentially what it means to be isomorphic. Okay. And then we talked a lot of time about linear maps between two vector spaces. This is the map that's structure preserving, that preserves the vector space structure. And similarly, if this linear map is invertible or if it's bijective, then we have this idea of isomorphic vector space. Just a small notation. Usually, this is a common one. Whenever you want to say that I have a map that's also linear, usually we put this, this tilde over the arrow. Okay, so this is just, a small indication that the map actually is linear. And last time we gave precisely what does it mean for a map to be linear. So just to recap what the vector space was. So a vector space, which is the so this triplet was simply a set, and it had two operations, one which is the vector addition, another one the scalar multiplication. And we should satisfy the fact that if you take the set V and the scalar addition, the vector addition by themselves, they make an abelian group. Okay, which means they should satisfy all of the conditions. Okay, you don't need to memorize them. Okay, once you work with them a lot, you know exactly what an abelian group is, and always you can go back and check what the conditions are. So this is just the short version of it. And also the map, which is the scalar multiplication, should also satisfy some conditions, and all of these conditions you can just summarize them by saying that this map is an action of the field on this group. Okay. Exactly what does this mean? It's exactly the definitions that were given last time. Okay, so all of this were omitted here. So this is just, the two-liner definition of what a vector space is. If you want to go through all of the definitions, go back to previous lecture and see them. An element, if you take just one element of this space, now this is what we call a vector. Okay, and this was the prototypical example that we gave last time. So just from the name where it comes from, what you know as a vector is a vector, okay? But what you also know as a matrix is also a vector, according to this definition, okay? So that's why forget about what you call a vector, okay, which is just putting some numbers, okay, in some, one after the other, and let's call this just an n tuple, okay? You just call them, and whether you write them like this or like this, it doesn't matter, right? Because they're just some numbers or some ordered set, some ordered array of numbers, okay? Think of it like that. So this is the ordered array, but now when we have the vector addition and the scalar multiplication, this is three together, you can do more stuff. You can take two vectors, I can add them, and I can get another vector. And of course, you visualize this as, a vector, and I get a third vector, right? So this is the scalar, okay? So this is the vector addition. The scalar multiplication is that you take a vector, you multiply by a number, everything gets longer, right? So this is the scalar, okay, multiplication. And of course, the identity element of this group, of this abelian group, is simply the zero vector. This is the vector that when I add it to any other vector, I get the same vector that I added it to. So that's why it's called, this is the zero vector. Similarly, we have the m by n matrices, and we have this, okay, component-wise. Okay, we do this for all of the components of this matrix. Is this clear for everyone? Okay. Then we went to linear maps, and we described linear maps in this abstract way. So we said that a linear map between two vector spaces over the same field K, which means that V and the plus, and so the green part and the purple part, so all of these two vector spaces, they are over the same field K. And we said they should satisfy these conditions, okay? So that, if I take two elements in the V space and I add them together and then I apply the A, I get the same result as first applying A to V1 and A to V2 and then adding the result, okay? So, and this is, the three conditions, right? So in the end, you can these are the two conditions. If you take them together and you just simply remove all of this, additional notation to identify which map belongs to which space, you get the usual, okay, equation that you're supposed to have seen before, okay? The definition of a linear map, okay? It should satisfy something like this, which is related to the superposition principle, as you mentioned last time. And then things become here interesting because I showed you last time that the set of all linear maps between two vector spaces, okay, is in fact another vector space, okay? So we can take the set of all maps, okay, from V to W, okay, and all linear maps, to be precise. We can take the set of all linear maps from V and W, and so this is a set, and we can give it a plus, and we can give it a scalar multiplication, which will make it by itself another vector space. So now we started from two vector spaces, which V and W. Each one of them has its own operations. Now we have a new vector space, which is L from V to W, okay, and it has its own operations as well. And now we had last time this abstract picture. Okay. Today, inshallah, this will be hopefully much clearer than last time. Okay, so we're going to see a clear example what all of this, okay. Again, an example of what they mean. Okay, but this makes sense in the abstract, okay, setting that we're discussing here so far. So L from V to W said it's the set of all maps where A is a linear map. Okay. And then we said that if we go from V to V, okay, so the set of linear maps from V to V, we call these the endomorphisms, the set of all linear maps from one vector space to itself. Okay, so this is simply the definition. And then we looked at an even smaller set inside of the endomorphism and inside of the linear maps. We called it the automorphisms, which is the set, it's the set of all A inside of the endomorphisms that also satisfy another condition that A has to be bijective, okay? You can write this, by the way, in two different ways. Check for yourself whether these two are actually the same. Are these two sentences, do they make sense to you? I can either say automorphisms is the set of all maps from V to W, where A is a linear isomorphism. Do you remember what a linear isomorphism was? It was a bijective linear map. But if I say it like this in the first sentence, I can only say A is bijective. Why don't I need to say A is also linear? Because I'm only looking at all of the A's that are in end of V. Right? And this is the picture that you have here. So automorphism is a subset of the endomorphisms. The endomorphisms are a subset of the linear maps from V to W. Is this clear? Is this picture clear to everyone? Okay. This is math. I know you don't have anything to calculate or to put on the calculator, but this is still, okay, the abstract setting that we have so far. Is this clear? Yes.
The addition and the multiplication only sit in the vector space and linear map, right?
Sorry?
Addition and the multiplication, only the operations that is in the vector space and the linear map should preserve these two operations, right?
So go back. You're talking about this definition. So a linear map between two vector spaces should satisfy these two conditions. Of each one. You see, each one appeared. You saw the dot, the circle dot, and the square dot, and the circle plus and the square plus, they all appeared in the definition. So it should respect the structure of both vector spaces.
They are multiplication and addition.
That's the name. That's the name. It's an operation. We call them, if you go back here, we call them vector addition and scalar multiplication. They are what you have in mind, okay? But they are more general than this. And the example is here. Is this what you call a vector addition?
Could be, but in different
is this what you call usually before taking that course? Is this what you call vector addition? No, but this is what we call here a vector addition. Okay, so that's the confusing part. So what is a vector? It's an element of a vector space. Full stop. Forget everything you know about linear algebra. Okay, unless I tell you to. Okay. You mean that in the end are between two vector spaces. Okay. They will have the same name, but they will look different. So we can make up something that looks, weird. Last time we did it actually between for the vector space of linear maps. We did it. All right. I told you what the plus, which was, I think it was the diamond plus, if you remember, and the diamond dot. We already did it. That's another example. We can make up with some, we're going to run out of, meaningful examples. And we're going to be going into exotic examples. And I don't want to go there. Okay. This is one of the statements that we mentioned last time without any proof. I told you that the vector space, the set of linear maps from V to W and also the endomorphisms can be made into a vector space. And I showed you last time the diamond plus and the diamond times. And these actually diamond plus and diamond times were defined point-wise. If you remember, we actually needed to go inside of every point and just, this is how we defined it on the maps themselves. Okay. And I told you, if you remember, that the automorphisms, if you give them the same operations, is not a vector space. You remember that? Okay. This is in general true, abstractly. And we said that the automorphisms, because this is a set of maps, there is one operation that we know that we can take two maps and give a new map, which is the composition. Right? We discussed it in the first lecture. I think in the second lecture. So the composition of two maps is another map. Okay, that's an operation between two maps. So if I take the set of maps, this set of maps, and I equip it with this composition operator, we said that it will make a group, and the group is called GL of V. But if you take the same operation and you give it to L, V, and W, which is this set and that set, they will not make a group. This is usually in general what you have. Okay? Now hopefully today you'll be convinced that this is true. Okay, by an example, but this is true in general. Okay, this is a general. This is a very important conclusion. Okay, this is far beyond this example or this the level we're at, which is groups and vector spaces. In general, if a set can be given a structure, which, for example, a vector space or group or manifold or Lie group or an inner product space and so on, which is that stuff that mostly we're going to be covering later or not even covering. So any extra structure, a subset of the set or a superset of the set, okay, does not automatically inherit the same structure with the same operations. Is this clear as a statement? This is, just some statement, some conclusion that you should take in general. And today you're going to have an example that, that will show you, this is really true. You're going to see it with your own eyes, inshallah. Okay, so this is the general conclusion that you should, take home message that you should take. Before going into some numbers, just your comfort zone, let's still remain in the abstract sense. And let's introduce one more operation, one more notion, one more object that's tightly related to vector spaces. And this is usually known as the dual vector space. So this is a new notion, new definition. The dual space, okay, so there's a vector between brackets, forget about it. So the dual space, which is what we're going to be calling it, it's a V star. It's dual to a vector space, okay, is very important, okay? Very, very important, especially in mechanics. And when I say mechanics, we mean rigid body dynamics, and later on we'll be see, okay, it will affect us in robotics. And usually people don't care about it in general, okay? And it has a lot of, consequences. First, an element of V is usually called a vector, but an element of V star usually is given the name a covector, okay, or a 1,4. And in mechanics, this statement is, just take it for now, okay, but it will make sense later on, inshallah, that velocity-like variables usually are vectors and force-like variables are usually covectors, okay? Doesn't make sense now, but later, okay, this will be clear, inshallah. So what is the definition of a dual space? So let V be a vector space over the field, okay? The dual space to V is defined as this. What does this mean? Is the set of all linear maps that go from the vector space V to the field over which V is defined. Okay. But you remember what we said last time? We said that we needed K. We defined L as the set of linear maps from a vector space to a vector space. But K is not a vector space, right? It's a field. It's trivially a vector space if you consider it over the same. If I consider K plus n times a vector space over K plus n times, so it's a field over itself, so it's a vector space over itself, okay, this is a trivial vector space. Okay. Is that clear? So you remember we said that Rn, okay, let's go back to this example. We said that Rn with the plus and the times, they make up a vector space. If n is equal to 1, what do you get? R and the normal plus and the normal times. That's exactly what I'm saying, okay? So if you just consider it like this, it's trivially, a field is always a vector space over itself, okay? So this is just a trivial example of what a vector space could be. So if you look at, if now we take any element from V star, let's call this element phi, alpha. Then alpha will be what? Will be a linear map from V to K. And this is what we call a covector or a 1,4. Okay? Is this clear? So alpha, if I pick any element from that space, from the space V star, I'm going to get a map from V to K. And this map is linear. Okay? Clear? Abstract definition, new object, we're just going to add it to our toolbox. Okay? To the field. Exactly. Exactly. Absolutely. Yeah. Now we're going to, so whenever I introduce a new object, I'm going to always be very precise. Later on, I'm going to be reducing a little bit the notation. So when I say, for example, that a linear map from V to K, you should understand what? That V and K here are understood in what context? Being as vector space, exactly. Okay. So not as groups, not as sets. Okay. So you can always imply it from the context. Yeah, okay, because you came late. So this means it's a linear map. So this is just a notation, means that the map is a linear map, just a shorthand notation. It's a common one. It's called absolutely, yes. Now this is a statement that, okay, will not make sense, but in general, this is true. You remember we said that LV and W in general is a vector space. And if I choose W to be K, I get another vector space. Okay. So V star is also a vector space. So I started with one V, and I got a dual space as we defined. It's a set of linear maps, which is also a vector space. Okay. And both V and V star, they have the same dimension. And this is something that doesn't make sense at all right now because we never discussed what is the dimension of a vector space. Intuit, no, not the same. Okay, it's not the same as the cardinality. Yes. What's multiplying? I'm saying according to what we said so far, you cannot define what a dimension is. But intuitively, you know what it is. If I give you n tuples, you know it has dimension n. That's what it means. It's different from the cardinality. Okay? And this is the picture. So we just augment the picture there. So now we had the LV from depth, L from V to W, linear mass from V to W. If I look from V to V, I have the endomorphisms. If I look from V to K, I get the V star. And if I restrict myself into the endomorphisms to only maps that are also bijective, I get the automorphism. Clear? So new object, okay, just an extra definition. Yes. Absolutely. Go.
Say that this set of linear maps LVW, we cannot say it is a dual vector space to the V star.
That's an excellent question. So the question is, if we said V star is a vector space, what if I remove everything here with the V and I put V star? Okay, I'm gonna get a new object. Okay, so a related question is, what is the star? What is the dual space of the dual space? The original vector space. So it's isomorphic to it. It's not the same, but it's isomorphic to it. Okay. So, but this you can show it on the side that the dual of a vector space, the dual of the dual. So if I take V star and I take the star of the V star, I go back to the original V. Okay. I can go back to it. It's isomorphic. Okay. You're going to have a new diagram. You need to look at another set. No, it's inside of the V star is only from V to K. If you replace the V and put the V star, I should put here V star, and this is another space W star, and so on and so forth. We're gonna have an example. I think it's next. Yeah, it's actually this one. Okay, and this is related to I think your question. Fundamentally, V and V star, they are two vector spaces that are the same. No, they have the same dimension, but are they the same space? No. One is a vector space, another is a vector space. That's cool, okay. But are they the same vector space? No. Objects here, okay, are vectors. Objects there are covectors. Okay. So they are vectors, but of a different kind. That's why we call them covectors. Okay. Not the same type of vectors that we have. And thus, because both of them are vector spaces, I can define maps between these two vector spaces. And I have four combinations. We looked at the endomorphisms, which are linear maps from V to V. But I can also have endomorphisms from V star to V star. I can also have linear maps from V to V star or linear maps from V star to V. So we have four possibilities. So we have the end of V, the end of V star. We have, these are called bilinear maps or bilinear forms. So it's another space of maps, and the BL of V star is a fourth space. So how many space of maps do we have? We have four. Okay, so I started with one vector space. We defined what the V star is, and now I can have four different types of maps between this. Okay. Now let's go slightly closer to Rn. Yes. End V star, BLV, and BLV star. These are four spaces of linear maps. Each one of them is on its own a vector space. Because L of V to W, with no matter what V and W are, of course, they are vector spaces, but I mean, in general, for general vector spaces, L of V and W is always a vector space. Okay?
Just to make sure, BLV and BLV star are inverses, right?
What does an inverse mean? No, different X. That's a very good question. Okay, that's actually a very good question. I think when you see here B that goes from V to V star, you saw here that actually this capital pi goes from V star to V. Then you say, okay, yeah, of course, it's the same, right? It's just the same map, but going back and forth. No, it's a completely different map. It's a completely different map. If I tell you, say, okay, Ahmad is not Muhammad, you say how? They are different people by definition. So this is a different map. The inverse is something else. Okay.
They have essentially the same elements in them.
They have the same domain and the same codomain.
V star will always have the same domain and same code.
These maps, these maps, so B goes from V to V star, and this set, so this map goes from V star to V. So goes from the codomain of this to the domain of this.
Saying is we are using the same vector spaces V and V star.
That's right.
For both the maps.
Yeah.
So V and V star have the same elements in them as vector spaces, as individual vector spaces.
That's
V
right.
has elements. V star has its own elements.
That's right.
So if I make a map, I can make one map which I call B.
Okay.
V to V star.
Yeah.
If I'm going from V star to V, it's still the same elements. How is it not the inverse of each other?
Because I'm not mapping the same element. Okay. You're talking about the space.
So could be not projective, right?
That's a very good question. That's actually the correct way to see it. But is it the way? No, that's actually, we're going to confuse ourselves, because you remember we said automorphisms? Automorphisms are a subset of these, not a subset of these. Right? We said that going back and forth, so if I have bijective maps, okay, from V to V, we call this the automorphisms. Now we need to define a new map, a new set, which is a subset of this. So this includes all linear maps from V to V star. If you want to have only bijective linear maps from V to V star, you need to restrict it a little bit. It's not here. It's actually a smaller set than the BL. The BL has all maps. It's possible, yeah, of course. Okay, if you need it, you define it, of course. Yeah. Now, if V is n-dimensional over R, yes.
Bijective map from V to V star and also from V star to V, then it would be the inverse of each other, both the bijective maps.
That's a very good theorem to prove. I don't know. But you should state it like this. If I have a general vector space, this is the quotation. For any vector space, is it possible, or is it only for a made-up example? That's the question. Check it and please let us know. I don't know, honestly, okay, whether that's the case or not. We said that V is an n-dimensional vector space over the field R. Okay, so when I say R here, what do I mean? When I say the field R, what do I imply here? R plus and multiplication. I'm talking about the multiplication and the multiplication, not just the set. And V star is also n-dimensional vector space over the same field. Then all of these four maps, if you take any element of here, you represent them by n matrices. So the question is, if I give you a matrix, how do you tell which one it belongs to? You cannot. You cannot tell. So this should give you a little bit of an alert. Is always representing matrices a good thing? The general answer is no, because of this fact. Okay? Throughout the course, we're going to be coming with very important, transformations, very important linear maps that actually are exactly have the n by n matrix representation, but they correspond to something completely different, because you need to look at it like this. Today, I'm going to show you, okay, hopefully, okay, if we have time, we're going to come to this point, and I'll show you in how can you actually see where, okay, what kind of object do you have? Is it this one or this one or this one or that one? Okay, later on. Now, okay, hopefully the confusing part, hopefully, okay, because if you get confused here, okay, this means that you're going to hate the linear algebra, okay, information that you have, and hopefully you're going to be triggered to relearn it. Okay? And this is my ultimate goal, hopefully. Okay. So we're going to look at a very special case, okay, which is V equal to Rn. And we're going to look at the field to be R. And what do I mean by that? What is the vector addition for Rn? The one that you know. Okay. So I take every component and I add them together. What is the scalar multiplication that we're talking about here? Also the one that you know. I give you some number and I tell you multiply by the vector. You take it and you multiply all of the components of the vector. Make sense? So I'm looking at a vector space V and the field R, okay, which is just R and the plus and the times, the normal one that you know. The dual space Rn star is the set of all linear maps that go from Rn to R. Make sense? By the way, this is exactly the same slides that were before. I just changed, removed V and the K. I put R, N, and R. That's it. And I would put some colors. It was very easy to make this slide, okay? You can prove, and this is something hopefully we're going to be doing it today. You can prove that any linear map must have the form like this. That when I give it any vector, in the end, the result, the number that I get should be written as the summation of one number, we're going to call it alpha 1 multiplied by V1 plus alpha 2 multiplied by V2, alpha 3 multiplied by V3, and so on and so forth, up until n, where n is the dimension of V, where n is the dimension of V in this case, okay? Because it's Rn. Okay? So remember, what is the V subscript I? Sorry, V superscript I. What is this? We said V is Rn, right? So I have x1, x2, x3, x4. You put them, one over the other. Okay? So this is the VIs. But what is the alpha i's? Some numbers. Okay? Where does each alpha I is a real number? In the field, except yeah, exactly. So it's related to the field, yeah. Now this one, you know it. Okay? This equation, if I show it to you differently, you will actually recognize it. You know it like this. Make sense? How do you put the alphas here as a? What do you call it? A row vector, right? So if Rn is the set of all column vectors that you're used to, what would be Rn star? The set of all row vectors. If you take one row vector and one column vector, I don't need to do anything else but just multiply this by that, row by column. There's only one row and one column. So it's this operation that gives me in the end one number. If I take a 1 by n vector multiplied by an n by 1 vector, this is not this vector, this is linear algebra. 1 by n multiplied by n times 1, what do you get? A 1 by 1, just a scalar. That's exactly what you have. So you see here, alpha is a map that goes from Rn to R. So a row vector is a map that goes from Rn to R. Make sense? Let's go a little bit further. What are linear maps between Rn to Rm? So let's talk about the vector space V, which is Rn, and another vector space Wrm, where n and m are not the same. Could be, but they are in general not. Equipped with the vector addition and the scalar multiplication that you're used to. The set of Rn to Rm contains all linear maps A from Rn to Rm. They have to be linear. And you can also show, in the same inductive reasoning, that, okay, this is just an extension of the previous one. The first one we're going to be showing it, but this one is just an extension of it. And if I have the linear map A and it eats a vector V, the result I get, which lives here, should be in Rm. The first element in Rm, okay, so the first element in this M vector will be written like this, and the second one will be like so on and so forth. Where Aij are now, also in R. Again, this is usually the common way that you understand what A is. So if you can take this Aij and put them into what you call a matrix, and you apply what you call a matrix multiplication, which is row by column, row by column, row by column, the standard operation. This is exactly a map that goes from Rn. So I started with an n vector. What did I end up with? An m vector. Okay, so this is an m rows and n columns matrix. But in the end, it's linear. Okay? This linearity was actually, you never even check it, because the whole course that you took before was called linear algebra. So it's assumed that everything is a linear map. Okay? But you can check for yourself. It actually dissatisfies the linearity condition that we mentioned earlier. Okay? Make sense? So what is Ln? So what is the L that goes from Rn to Rm? It's the set of all m by n matrices. Okay? Now let's see whether this makes sense to you. Check it. Make sense? If V is Rn and W is Rm, so this is the set of all M by N matrices. And the V star is the set of 1 by N matrices. So this is just the case M is equal to 1, right? And the endomorphisms are the set of all maps, all linear maps that go from the vector space V, which is in this case Rn, to the same vector space Rn. What do you call this? You call them the square matrices, N by N matrices. But what are the ones, if I restrict to the ones that I can go back and forth with the map, what do I get?
Determinant is not here.
Exactly. So there should be, if I take any element from here, okay, from this one, and I can go back and forth, this means that its matrix representation, okay, has an inverse, which is equivalent to saying that the determinant is not zero. Okay? Makes sense for everyone? This is as a set. This is only as a set. Make sense? So we said that Rm times N matrices with the vector addition, which is what you call matrix addition. So here the plus is actually what you used to know as matrix addition. I take two matrices and I add them together component wise. And the scalar matrix multiplication is what's known, okay, is what the circle dot. So I give you some scalar and I tell you multiply it by a whole matrix. What do? You take it and you just, you duplicate it and you multiply it for every element, component wise also. If I take these two operations and I give them with Rm times N, they have a vector space structure. That's actually one of the examples, that we saw earlier. And if I choose M and M to be the same, I just look at square matrices. This also has a vector space structure. A vector space structure, a vector space, one of the conditions that it must have was, you remember, the zero element. Remember? What was the zero element? What was the zero element of a vector space? It was the element that when you add to it any element, I get the identity in the addition. Exactly. So it was the zero element, right? It was the zero element, something that I add and I get the same element that I added to. But here we're talking about the set of maps. So what is the zero element here? It's a zero, the zero map. So the zero map is that if you give it any vector, it will give you, zeros. The exactly, the tuple of n zeros. Okay. If this one, in this case, it will give you a tuple of m zeros, and this one, it will give you a tuple of n zeros. Okay. If you go back to the example, this was actually the zero matrix. So in this case, so the zero element is the matrix is the m by n matrix of zeros, and in this case, it was the n by n matrix that had all zeros. I multiply it by any vector. What do I get? Zeros. Make sense? But the zero map, okay, does not have an inverse, which means that it's not invertible, which means that it's not in the set of automorphisms, which means that this is not no. It's not a vector space. It does not have you remember we had certain conditions. One of them, it only was one of them, that it needed to have the zero element. Okay. Whenever you're checking something is not, so always take it like this. Whenever you're checking something has a structure, okay, this is actually the assignment you're going to be having, okay, today, okay, maybe tomorrow. Whenever you want to check whether something has a certain structure, you need to check whether it satisfies all the conditions of the definition for all elements that's inside. Okay. And if you want to show that something does not have that structure, what does it suffice? To only give one example that, okay, and one condition that it does not satisfy, which means that in general it does not satisfy. So here, in this case, I'm just giving you one of the conditions that's not satisfied by the automorphism set, which means that it's not a vector space. We cannot make it in the vector space. So this is the example. This is the proof of the, this is not a proof, okay, but this is just an example of the statement I made earlier. In general, that's the case. Okay?
It breaks the addition in the field.
Exactly. Absolutely. Make sense? Remember, we said something else, not about, in addition to the vector space structure, what was it? We said something about this having a group, but these two don't having a group. Remember? What's the proof of that? Now let's see it in this example. So the automorphism, let's define the cross time, the circle cross, which is the matrix multiplication. I give you two matrices and I told you multiply them by each other. You know how to do it, right? Row by column, row by column, row by column, and then row by column, and so on. If I take this operation and I give it to the set of automorphisms, we have a group. Okay? And this is actually the group that we introduced earlier, which is, we called it the general linear group. You remember what the general linear group was? It was the set of all n by n matrices that are invertible. That's exactly what we have here. The set of all matrices that are invertible, but we cannot talk about a group alone, okay? We cannot talk about a group unless we specify what is the operation, right? So you see here, that's why the pair together, usually it's implicit, okay? The automorphism is the set. When I give it this matrix multiplication, we make it into the group, and this is actually called the general linear group. This is actually the GL of NR. Okay. Now, again, I'm going to show you as a condition that's not satisfied by these two, which does not make them into a group. Okay. Let's take the endomorphism first. One of the requirements for a group is that every element should have a inverse. You remember that? So we're talking here about the set of maps, which means that every map should have an inverse, which means every map should be bijective. However, the endomorphism is a bigger set than the automorphism. Why? Because it includes linear maps that are not bijective, and thus it's not a group. Make sense? Can we apply the same logic for this one? Check it for yourself. Think about it. You cannot apply the same logic. Think about it. Think about it. If I give you the set of, what was this space in our example here? It was the set of m by n matrices. And if I look at the set of m by n matrices and I give it the matrix multiplication, what can I say about that? It does not even exist. It's not even well defined. Why is that? If I give you an m by n matrix and an m by n matrix and I tell you multiply them together, can you do that? Not, it's impossible. If you can do it, do it. Okay, so there's no necessity about it. It's impossible. I give you any two m by n matrices. It's not defined. The map we're talking about, which is what you already have in mind, the matrix multiplication, okay, it doesn't make sense here.
Apply to the matrix multiplication.
Yes.
Another operation. It can be.
That's right. Yeah, absolutely. You can make it. That's right. You can try to work around and make it into a group. That's why the statement was, if you go back to the conclusion, is that the same operations. If I can give this the same operation and make it into a group, and take the same operation and give it to that, it's not necessary that this will be a group as well. This is the example here. And if I take the same operation and I give it to a superset of these two, it might even not be defined, the operation itself. So this is a clear example of the general statement, okay, that was mentioned. Does this make sense? Okay. Now I'll just give you a small example of a map that's not linear between two vector spaces. Okay. So you remember this diagram? This was already including all of the maps that are linear between two vector spaces. So a normal question would be, if you're studying, late at night and you start to get, dizzy with all of this stuff, and you might say, okay, what if I have a map from V to W that are both vector spaces? Can it be not linear? The answer is yes. This is an example of a map that is not linear. So it's not even within this whole set. It's actually outside of the set. This is an example of it. We're going to be defining the map capital psi that goes from Rn to Rm between the two vector spaces that is defined by this. Okay, this is the formal definition. If you want to see it immediately, okay, in component matrix vector notation, this is how it looks like. I take a vector, I multiply it by a matrix, and then I shift it by another vector. So A and B, they make the map psi. Does that make sense? So I get A of V plus V. This is not a linear map, and it's very easy to see it. This is actually the proof down there. One of the conditions of being a linear map is that if I take some scalar constant and I multiply it by the V, the vector, I should get in the end gamma multiplied by the map acting on the vector alone. You remember this condition? So we had two conditions in one. I need to multiply it by a scalar, and I also needed to add any other condition, okay? And any other vector. Okay? This was the definition of a linear map. So here we talk only, I'm not checking for the addition, I'm only checking for the scalar multiplication. Remember this idea of, I need to only show one condition is not satisfied. So this is the condition that's not satisfied, clearly because, okay, A itself is a linear map for sure, but the B itself, I'm not, okay, the shift there. One of the very easy ways to check something is a linear map or not is that the zero element of V should be always mapped to the zero element in W. So this is actually an implication of this, okay? So here, if I give this the zero element, if I give here V to be the zero vector, so what do I get here? Zero, but plus the B's, what do I get? I get the B's. So I'm not mapping zero, I'm not going from 0 to 0. If we go back to the definition of the linear maps in general, which had this form, this one, if I have the 0, I will always get the 0, no matter what the A's are. Okay? So this is actually one of the conditions, one of the like corollaries, one of the implications of having actually a linear map. Sorry? Exactly. It's a very good point. Is this a nonlinear map? I said it's not linear, but is it nonlinear? It's neither nonlinear nor linear. It's just a shifted map. So this is actually a very special one that appears all the time. We're going to be using it later on, inshallah. And this is why it's in the gray area between linear maps and nonlinear maps. Nonlinear ones, you need to have a nonlinear operation, which is something like a square, a sine, and stuff, all of this stuff. Okay, this is like a very special type. Okay, of a it's like the most well-behaved. This is just an intuition, it's like the nicest it's the nicest maps that is not linear. Okay, without we could just call it an affine map, and you see it all over the place. Does this already ring a bell to you? Have you seen something like this before? Where? Well, what else? State space AX plus U. So you have something there. We're not talking about it. I just have you seen it before? Yes, it looks like it. Okay, but did we talk about it? No. Okay, so no more questions about it. Let's see, how much time do we have? Okay, any questions before we move on? Okay, so far we started by abstract concepts. Okay. You got very mad. I gave you some examples. I see you're all smiling now because that's good. Okay, but now you see the whole point of actually, you cannot mix the both. Okay, there is something called the abstract vector spaces, and they make sense. Okay? And now we have the special case only, which is the linear algebra, everything you know about. And it's very dangerous to only know about this because you don't know, about this general stuff. Okay. And I'm going to show you why now it's actually very dangerous to do that. Okay, that only to work with what you call vectors, which is the n-tuples and their corresponding matrices. Okay? Why is that dangerous? Okay, why you can actually make mistakes if you don't know about the rest of the stuff. And hopefully this will link both. First of all, can you work in real life without knowing all of that stuff? The answer, unfortunately, is yes. Because of this very simple okay, theorem, okay? I'm not going to prove it, it's just a statement, okay? It's very, I'm going to actually show it now. It's a very intuitive, okay, theorem. If you give me any finite dimensional vector space, I can always find the corresponding Rn that's equivalent to it, isomorphic to it. So I don't need to know about this abstract stuff, to do calculations at least, because in the end, working in this abstract way, I just can go to Rn. What is the relation here is that the Rn part, that's equivalent to any vector space is simply known as the components of the vector. Okay? So the components of the vector are the Rn, but the vector itself is something that's abstract. Okay? And this is usually where things get confusing, okay? Because you can make some, assumptions and you get some conclusions that are not general enough, because it all depends on the basis that you chose. So yes, of course, they are isomorphic, provided you've already chosen what the basis is. Okay, this is the formal definition of what the basis is. Okay, you need to actually provide it. We need to actually spend some time here, but I'll just give you the intuitive way. You already know it. Okay, from the linear algebra. We're just going to go to the board now and just look at it. Okay, formally. Okay, sorry, intuitively. But this is the formal definition. So a V, let V be a vector space over R. A basis S. Okay, so S is a basis. We call it a basis for a vector space. Okay, first, what is S in the first place? It's just a collection of vectors. Very important. It's a collection of, what does a collection of vectors mean? It's a set of vectors, but not any vectors. They are selected vectors. This is very important. So V had all of the vectors, but S has only specific number of vectors. Exactly. Specific vectors, by name. But not any vectors in the vector space are enough to call a basis. They need to satisfy some conditions. These conditions are simply these two lines. And they already ring a bell from the linear algebra. These bases, this collection of vectors, they have to be linearly independent from one another. Okay, that's the definition. And they should be able to generate V, the vector spaces that we selected them from. This is the formal definition of what linear independence is. This is the formal definition of what generation is, okay? I'll leave it for you at home to read. What?
We have a set.
Yes?
Consists of elements. Specific elements of this set makes a vector space?
No. This is just a collection of vectors. Okay? This will be clear now, okay, in the board. So let's go to the board. Okay? You have this previous part at home. You can read it as much as you can. Okay? And you will see that I'm 100% sure you've seen this before in your linear algebra course. Okay? It's just that you skipped it very quickly because there are actually easier ways to calculate. For example, linear independence, you all know that you can put the vectors in a matrix and you calculate the inverse of it or do the, I don't remember even what was the name. I think it was a Gauss-Jordan elimination, something like this, Gauss, yeah, I don't remember even, okay? But this was the formal definition. So I'm going to show you now here a box. Okay. So this is a 3D box that contains, this is the vector space we're talking about, V. Okay. What is this a vector space of? It's a vector space of vectors. Okay. So I have inside a collection of stuff that look like this. Oops, that should not be. Okay. So inside of this V, I have a collection of stuff that look like this. Vectors. So all of the yellow ones are simply the collection of vectors, is what I'm going to call here the abstract vector. Okay. In real life, this is a vector. 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 Okay. If I tell you in which direction am I moving right now, please make it with your hand. Okay. Which direction I'm moving in? Okay. You see the same vector. Okay. You all have described my movement in the room, right? And it doesn't matter where it was. Everyone made it with his own hands. So it doesn't matter where it is. This is actually called the free vector. Okay, so this one, all of the one in U, so this is actually the set of free vectors. Intuitively, it is a vector space, okay? Because simply I can multiply by any number. I can make the bigger or smaller. For example, I can walk faster or slower. Okay, so you can describe how fast I'm moving. So this is faster or slower. So if I'm moving in this direction, I'm moving slower than this in direction. I can also take two directions, which means that if I move first in this direction and then in that direction, it's equivalent to moving in this direction. You see, am I using any numbers? They make sense on its own, abstractly. So this is the abstract space. Now we're going to be choosing three particular directions in this abstract space that we're going to be calling them E1, E2, and E3. And if these three, first of all, the dimension that I have, so okay, forget about what dimension is, but these three, this collection, you can show, okay, intuitively again, in the same way that we're doing right now, that any V in the vector space V, any vector, any one of the yellow vectors in this space V, I can write it as some number multiplied by E1 plus some number multiplied by E2 plus some number multiplied by E3. Okay? So any direction, inside of this room, if I give you any direction, you can always decompose it into three elementary directions, which is simply what you call a basis. So these three together, so if I take the set that has only E1, E2, and E3, we can call this the set S, and we say that this set is a basis for the vector space V.
E1, E2, E3 are directions.
Are three vectors inside of this vector space, and because we're talking about directions now, yes, of course, they are directions. Directions. They are this is the abstract space V is the space of all directions inside of inside of this room. So this is the room I draw, and I'm giving you all directions, and you can represent them by these three numbers. Where actually VI is simply a real number, where I goes from 1 to 3. So I can be 1, can be 2, can be 3. And I have three numbers. I'm sorry, this is a mistake. I'm going to put the index up. And okay, recognize here that this is actually on purpose, that indices for these numbers are up and indices for these vectors are down. So V is a number, E's are vectors. Yes. Sorry? We did not talk about it yet. Okay. That's still ahead. Any questions so far? Make sense? Clear? Okay. Now, are these three linearly independent? If you take these three and go back to the check, that we did, you'll see that it is true, abstractly. If you see that, do these generate V? Okay, if you go back to the conditions, actually, this equation is simply, okay, that we say that because all V's, okay, all vectors in the capital V in this space can be written as a linear combination like this. This means already that S, so V is equal to the span of the set S. Okay, so this is just a way to say this statement. So if V is the span of S, it's another way of saying that S generates V. And it's another way of saying that if I take any element in V, I can write it as a linear combination of some numbers, okay, that in terms of the e's that I chose? A very important question. If I chose these e's and someone else chose this to be his E1, I'm going to call it tilde. This is his E2 tilde and E3 tilde. And I define a new set, let's call it S tilde, that has the vectors E1 tilde, E2 tilde, E3 tilde. Can S tilde also generate V? Or in other words, can S tilde also be composed of bases for the set V? In general, yes. And if I write it like this, I'm going to be able to write the same vector V. This is very important. The same vector V as the linear combination. We need to remove this a little bit. No. So now I can write this as the linear combination of new numbers. I'm going to call them V1 tilde multiplied by E1 tilde plus V2 tilde multiplied by E2 tilde plus V3 tilde multiplied by E3 tilde. Same vector, different bases. I'll tell you what I mean by that right now. So, could you make your hand like this? Could you make your hand in the back? Yeah. So, so this is your positive x direction. This is your positive x direction. Am I moving with a positive number, okay, positive velocity or negative velocity? It depends on the reference. It's the same person moving, okay? Same motion, same abstract vector, but different numbers, just because the basis is different. Okay. And now you see, okay, if you give me any vector space V, okay, which has all of the elements V, I can always give you, okay, I can always define a map that will give you it's annoying. Can always give you V1 up to Vn. Okay. And I'm going to be calling this, I don't know, V with an arrow, maybe, or let's call it V with a box, or let's call it capital V. Sorry, sorry, not capital V, like bold V, whatever. But all of these are actually in Rn. Is this map always possible? Yes. What is this actually map? What did we just do it now? What is actually this map? It's the basis. So here, if you tell me what the bases are, I'll transform any vector, any abstract vector, which in this case is my motion, my direction of motion in the room. I'm going to transform it into 3 numbers, which are V1, V2, V3, or V1 tilde and V2 tilde or V3 tilde. Okay. So in the end, I can always give you a number, which in the end I can always give you an Rn if you choose a basis. So this actually was the basis. I can map, any finite dimensional vector space to its basis, to an Rn, provided you tell me what the basis is. So the statement that I told you earlier, that indeed every vector space is isomorphic to Rn. So anything I do with the vector space here, okay, as a vector space, I can do it with Rn, is because of this basis. Okay? And now because the basis, it depends on, these numbers, the biggest problem, okay, that you have, okay, in engineering, in robotics, is that you talk about the numbers and you forget about the basis. I'm pretty sure the first time you were introduced to linear algebra, you've seen something like this. V is equal to Vx, x hat, Vy, y hat, vz, z hat, right? Or instead of the x hat and y hat and z hat, you have I and j and k, right? Cartesian choice, right? And you know what the Cartesian is. This is x, this is y, and use the right-hand rule and talk about the z. Make sense? But then you said, okay, this is a very complicated way. Let's forget about it. And from now on, this is actually what I talk about: Vx, Vy, and Vz. And then you say, yeah, this lives in Rn. Very happy. Let's do stuff. Are they the same? What is missing from these two formulations? The basis. Okay, they depend on the basis. We're done. Okay, so there's still more. Okay, so. Okay, I was hoping to finish it, but actually I think there are more important stuff. So if you want, I'll open it to vote, okay? Do you want to have a third lecture on vector spaces to really understand this, or is that enough? Enough, but we're gonna go to another topic in math, so we're not done with the math, okay? So you either take one extra vector space lecture, or let's go to another structure. Let's raise hands. Who wants an extra lecture on vector spaces? Okay, so done. We're gonna have a next lecture, inshallah, an extra one on vector space. Yes.
It's not only Rn is a vector space. It has cinematics itself that we know is vector space.
Absolutely.
Basis for these.
Absolutely. Excellent question. That's actually the next thing what we're going to be doing, which is next time. First thing we're going to be doing next lecture. Yes, you can have basis for any vector space. So the question was, we said that the vector vectors that you already know about, okay, these are the bases of them, okay, and they make sense because, okay, this is already how we know what the base is. But we said that any vector space can have a basis, which means that the vector space that has n by m matrices also has a basis. What do they look like? That's the question. Okay. I think we have in 1 minute. There's something that we mentioned today. Let's just wrap up with it. What is the dimension of V in this case? 3. Okay. The dimension of V. So what is in general the dimension of a vector space? It is simply, it's defined. If you remember, we mentioned, I told you, we talked about it earlier, but we never defined it formally. The dimension of any vector space. So the dimension of any vector space is simply defined as the cardinality of any basis. Okay? Of the basis. You see? So in the end, if I can find 3 linearly independent vectors in which I can write any other vector in terms of these, then we call this a basis. And because I have found 3 independent vectors, the dimension of V is S. So the dimension of V is the cardinality of it, which in this case is 3. Next time, I'm going to give you an example of a 3 by 3 matrix that has a vector space structure. It's a special type. It's not a general 3 by 3 matrix that has a vector space structure, but has a dimension of 3. So it's a 3 by 3 matrix that has a dimension of 3. I'm going to give you another example of a 3 by 3 matrix, okay, that has the dimension of 9. More on that later, inshallah. Okay? Jazakum Allah khair.
Basis.
It means it has 9 bases. Absolutely. Exactly.